Hi students, in this lecture I am going to discuss problems from Irodov. Let us see first one. A horizontal plane supports a plank with a bar of mass 1 kg placed on it and attached by a light elastic non-deformed cord of length L not equal to 40 centimeter to a point O as shown. This is a cord and you can see this is a plank and this is a bar. Okay. The coefficient of friction between the bar and the plank is 0.2. The plank is slowly shifted to the right until the bar starts sliding over it. It occurs at the moment when the cord deviates from the vertical by an angle theta equal to 30. Find the work that has been performed by that moment by the friction force acting on the bar in the reference frame fixed to the plane. So in the reference frame fixed to the plane, that means it is ground frame. Okay. So we have to calculate now work done by frictional force. And key points are plank is slowly shifted. Okay. This is the one key point. And when the cord deviates, that means see at which instant the bar starts sliding. That is when that cord makes angle 30 with vertical. So these are now key points to start the problem. Let us see. Let's first see the given diagram. So there is a cord. This is now cord, elastic cord. This is a block. He's saying it is a bar. Okay. And this is now plank. And this is now horizontal plane. Okay. So now here, so we are moving the plank by applying some force. We are moving the plank. It's a condition given that the system is moving slowly. You can see here what is given. Okay, first of all, see length. Length L naught, which is equal to 40 centimeter. Next. And next one, new value 0.2. The plank is slowly shifted to the right until the bar starts sliding over it. And this happens when theta equals 30. Right. Let us see. Now what we can do. After some time, we can say string makes an angle that is 30 with vertical. This is now position of the block. Okay. And this makes angle 30. Right. Now see what we can do. First of all, focus free body diagram for the bar. Coming to for the bar, I am drawing separately. This is a bar. Because of the elastic cord, elastic force will be like this. If x is elongation, spring force will be Kx. And I can take one component now vertically upwards. This is Kx. This is now 30. So Kx cos 30. And this is Kx sin 30. Kx sin 30. And mg vertically downwards. Frictional force. It moves because of frictional force. And that is now started because no slip. Now see what we can say. Condition given that until the bar starts sliding over it. So we have to calculate now work done by frictional force. Now key point is it is moving slowly. So here what I can say is delta K equal to 0 for the bar. That means net work done on the bar equal to 0 because moving slowly. Therefore delta K 0. Now see how many forces are acting on the bar. mg downwards, normal reaction upwards, but displacement is along horizontal. Therefore, because of gravity, because of normal reaction, no work is done. Remaining is only because of frictional force, work done by frictional force. Next, work done by spring force. Sum of these two should be equal to 0. Okay. Now we want to calculate by frictional force. So by frictional force, work done is equal to negative of work done by spring force. Okay. Now by spring force work done, that is equal to change, or I can say directly, we are having elongation the cord. Okay. There is now elastic potential edge. Initially it was 0. Therefore, this is equal to half kx square. So work done by the frictional force is converting into the elastic potential edge. Okay. That means now we have to focus what is x and what is k. So I hope you got clarity here. Only by frictional force work is done and by spring force work is done. Sum is equal to delta k, that is 0. So by spring force by frictional force work must be equal to increase in the elastic potential edge, right? Now from this, first of all, we have to focus what is k value, because coming to x, it is directly known. See diagram carefully. In this triangle, this is now adjacent side, which is equal to 40. That is L naught. This is now present length, L naught by cos 30. Okay. That means x value, elongation is equal to L naught by cos 30 minus L naught. Okay. So it is L naught into secant 30 minus 1. So it is x value is known. So x value is known. Now we want k value. To find k value, we are given one condition. You can see that it starts sliding when angle equal to 30. Now see carefully. Here, this is now static friction. Its maximum value is now limiting friction, right? Limiting value. If kx sine 30 is able to balance that frictional force, or you can say when it is about to slide, then what happens is frictional force becomes limiting value. So I'm writing here limiting value mu into normal reaction. See carefully, in this normal reaction will be this is mg normal reaction upwards. If you take force equation along vertical, the sum of these two is balanced by mg. So n equal to mg minus kx cos 30 mu into normal reaction. This limiting friction is balanced by kx sin 30. Okay. So from this, we are supposed to calculate k value because in this x is known. See k value how much? So k equal to see how much we can write here. I can take this one to right side. Then I can take kx common. Remaining is now this is a kx into sin 30 plus mu cos 30. See carefully once. Kx, I have taken common sin 30. I have taken this one to right side. So mu into cos 30. That is equal to mu mg. In this x value is known. Remaining all values are known. So from this we are going to get k value. Okay. So from here k value is known and from here x value is known. Substitute those values in this one. Then we get increase in the deformation potential edge, or you can say elastic potential edge, which is equal to work done by frictional force, okay, on the bar, right? So I hope you got the clarity. Let us see next one. A smooth, light horizontal rod AB can rotate about a vertical axis passing through its end A. About a vertical axis passing through its end A. The rod is fitted with a small sleeve of mass M attached to the end A by a weightless spring of length L0 and stiffness K. Stiffness means it is spring constant. Okay. What work must be performed to slowly get this system going and reaching the angular velocity omega? Okay. Right. Let us see how to start the problem. So first make a diagram. There is a massless rod given smooth light horizontal rod. Rod is horizontal. Imagine we are seeing from the top. Then axis will be, it appears just like a point. Imagine this board is now horizontal plane and we are seeing from the top. So this is now axis. Okay. The axis appears just like a point because we are seeing from the top. Next. Given passing through its NDA. This is now NDA. Next, the rod is fitted with a small sleeve of mass M attached to the NDA by a weightless spring of length L0. We can see spring here. A spring like this whose length is equal to L0 attaching one sleeve. Okay, its mass is here. This length is L0. What work must be performed to slowly get this system going and reaching the angular velocity omega? Now you can see when we rotate this rod, this spring will elongate. Let us say elongation equal to x. Elongation equal to elongation equal to x. Let us say it is now, this is now location of the sleeve. This elongation is x. Now focus. This sleeve is following circular path. Now see who provides centripetal force. So because of elongation, now spring force is there, which is providing centripetal force. Okay. So centripetal force is given by spring force, that is equal to m into r. Radius will be L naught plus x, m r omega square. Okay. So we have taken force equation. From this we can calculate elongation equal to kx. Take m x omega square left side. Then it is see what we can write here. Kx, we want to take your take x here, remaining k minus m omega square. Cross check once. We have taken m l naught, m x omega square left side. So m omega square x, right? That is equal to m l naught omega square. So from this x value is known, elongation of the spring, m l naught omega square upon k minus m omega square, right? Now focus, work done. Here, if you observe carefully, initially for the sleeve, no kinetic energy. Sorry, for this one, no kinetic energy, and for spring, no elongation. Now, spring is having elongation. That means it is having elastic potential energy, means spring potential energy. Now, sleeve is moving, it has a kinetic energy. And we have learned that by external forces, work done is equal to delta K plus delta U. That is delta K half mv square, delta U, that is a half kx square. That means if you think in terms of energy, there is a gain in the kinetic energy. Initially, there was no kinetic energy. Now, kinetic energy is there. Initially, no elongation, no compression, means no spring potential energy. Now, spring potential energy is present. So, sum of these two energies is because of work done by external force, right? Now, see in this half kx square, k, it is given x value that is known. Substitute that. Coming to v, it is now following circular path of radius L naught plus x. So v equal to r omega, and r value L naught plus x. We got the value of x here into omega. That means now v value is known. Substitute v value here, substitute x value here, then we get our answer. Okay.